Hello everyone, my name is Zhenghao Peng. I'm supervised by Professor Bolly Zhou here at UCLA. I'm super happy to share our recent work accepted to Neuro 2023 as a spotlight poster. In this work, we develop a new policy learning algorithm that can learn without reward with human in the loop. So let's start it by the reinforcement learning. Reinforcement learning is a popular choice of policy learning algorithm. In reinforcement learning, there exists an agent interact with the environment. But those interactions can lead to some issues. The first is the safety concern. Especially during the initial training stage, the agent might demonstrate some random behavior that is undesired and can lead to some unexpected outcome. So could we develop a new policy learning algorithm that can avoid those safety concerns during the training time? And the second is the sample efficiency issues. We require a lot of data and a lot of interaction between the agent and the environment before the agent can achieve high performance. So we want to develop a new policy learning algorithm that can achieve higher sample efficiency. And the third issue is the human alignment. We need to develop a new reward function to inject our human preference and human intentions so that the reward function can induce a policy that can align with human preference. But this process is typically really laborious and can cause many human engineering efforts. So in this work, we focus on the human-in-the-loop policy learning algorithm. Here I quote, the ultimate source of information about human preference is human behavior, from computer scientist Stuart Russell. So we consider the setting of human active involvement. In this setting, the human behavior is the interventions and the demonstration. So we invite a human subject into the loop between the agent and the environment. And the human subject is overseeing the process of the agent exploration. And the human subject can determine whether or not it wants to intervene into the environment and provide demonstration. So adopting this setting, we propose Proxy Value Propagation, PVP, which is an efficient policy learning algorithm without reward. And also PVP learn from those active human involvement. So we start by demonstrating how we collect the data. During the training time, we invite a human subject to control the object with the agent together. There is a button around those control devices. So when pressing the buttons, it indicates that the human subject wants to take over the control and provide demonstration. You can see that after almost 10 minutes of training, the agent already learned some primitive driving skills in those environments. And human intervention becomes sparse. After 20 minutes of training, the agent already learned and solved this task. You can see that the agent can run in the environment without any intervention from the human subjects. So how we learn from those active human involvement? The key concept here is that we introduce a Proxy value function, and we want those Proxy value function to reflect that which action is more preferable to the human compared to the action that is not preferable to the actions. To the human subjects. So in the human involved trajectory, we not only record the human action and apply those human action to the environment, we also record agent actions. And we want our Proxy value function to assign higher values to those human actions and assign lower values to those agent actions. So to achieve this, in those Proxy value objective here, we start by regressing those Proxy value and assign +1 values to the human actions. And vice versa, we also trying to assign the -1 values to the agent actions, AN here. So by using this objective, we're trying to let our Proxy value function regress, assigning a higher value to the human actions and lower value to the agent's actions. And we also use temporal differences objective to try to propagate those information to the whole state space. Compared to the traditional TD objective, here we remove the reward term because we don't receive any reward from the environment. So combining the TD objective and the Proxy value objective, we now achieve the objective to train the Proxy value functions. At the meantime, we will also using traditional value-based RL method to train a policy using the proxy value function. Even though our method looks so concise, our method can achieve superior performance in various tasks with various control devices. So in this four environment, you can see that our method achieve more than 10 times improvement in the training efficiency compared to the RL baseline. And we can use keyboard, steering wheel, and gamepad as the control devices. In the paper, we not only demonstrate that we can achieve better agent performance, but we also demonstrate that we can achieve better training time and test time safety performance. And we also show that by conducting a user study, we show that by using PVP, we can achieve better user experience compared to other human-in-the-loop method. We also apply PVP to the like a robot environment. So in this environment, the action space is so high that the human subject cannot directly control the object, control the robot. So we first train a low-level go condition RL policy in the environment without obstacle. And then we use PVP to train to assign the go to those go condition policy. And you can see that the PVP can train high-level controller for those low-level go condition RL policy. And our method can also learn the performance like a robot in this environment. Note that here the input is the depth camera, as we're using a CNN to process those observations. This work introduced Proxy Value Propagation (PVP) as an efficient human-in-the-loop policy learning algorithm. We can achieve higher agent performance, we can achieve almost zero training time safety violations, and very great test time safety performance, and our method is more human-friendly compared to other human-in-the-loop methods.